Yeah, teaching right now. Just started. Done at 3:15. All right, love you, babe. Alrighty, gang, welcome back. Sorry for that. Today, what are we doing today? Last time we introduced L'Hopital's rule. We talked about indeterminate forms and L'Hopital's rule. Today, what I'd like to do is get just a smidge more practice working with L'Hopital's rule and indeterminate forms, because it's one of those things I find we always need as much practice as we can get. But then the meat of the day today is sketching curves. We're here, we're going to do the full thing, where we're going to try and sketch some curves using the guidelines laid out in section 4.5. And then the last little thing I want to do here is introduce the mean value theorem, which is a fun bonus topic of sorts. It is a useful and somewhat deep theorem. In our setting here as Calc 1 students, the mean value theorem is more of a curiosity. But in a slightly more grown-up math class where the objective is not so much to do calculations, but to prove theorems, the mean value theorem is an incredibly powerful tool that you can use to prove lots of other theorems. But we've got quite a bit to do today, so let's go ahead and start getting it done. This is MAC 2311, section 004, which is a Calc 1 class, and the date today is the 2nd of March, 2022. Today, I would like to solve a few more L'Hopital's rule problems. And then we're going to cover section 4.5 on curve sketching. And this is one of those really great sections where kind of all the shit we've been doing comes together into a single thing. And you'll be amazed at two things. One, how fucking long those problems take, but also how beautiful the results are. For so long in all of our algebra classes, we've had to memorize graphs and be like, okay, I can shift this or flip it or move it around, and all this bullshit about sine waves and changing the period and stretching and horizontally shifting the phase angle and all that stuff is gone now. No more memorization necessary. You can, from first principles, come in and sketch a beautiful graph of just about any function using only the tools we've discussed here in Calc 1. And I doubt there's time for it today, probably mostly on Friday, but maybe we'll talk about MVT, which is the mean value theorem. So that's the plan. Last time, when we were looking at L'Hopital's rule type examples, we saw a handful of indeterminate ratio problems where as soon as you try to plug in infinity or whatever, you get 0 over 0 or infinity over infinity. There are some more subtle things like that where you don't get your indeterminate ratio right away. We saw, I think, just one indeterminate product problem, and we saw one indeterminate power problem. So I'd like to expand our repertoire of those kind of weirder indeterminate forms. So to that end, that's not fun. Let's do something fun. Yeah, this is a good one. So this is a good warm up. Calculate the limit as x goes to infinity of the natural log of x divided by the square root of x. This is something that came up in my Calc 2 class this morning where they're working on infinite series. And before we dive in with any of the mechanics here, I want you to think about this with me for a second, because it is not entirely obvious what's going to happen here. Even if you say, remember the graph shapes of both of these functions. So I'm going to pull up Desmos. And I'm not going to graph that ratio. I'm going to graph the numerator and denominator separately. Here is ln x. And the square root function is surprisingly similar, right? They have the same sort of concave down, but unbounded growth. Both of these functions grow forever and ever and ever, right? They both go all the way up to infinity as you walk off to the right, but they both grow very slowly. That's that concave down thing. When we're asking about the ratio ln x divided by the square root of x, what it really comes down to is who grows faster, right? They both grow slowly, but does one grow slowlier? If the natural log grows faster than the square root of x, then I would expect this limit to be positive infinity. If the natural log grows at about the same speed as square root of x, then I would expect this limit to come out to some finite number. And if the natural log grows slower than the square root of x, then I would expect this limit to come out to 0. And thinking about growth rates is a great way to try and understand L'Hopital's rule. Because what does L'Hopital's rule say? It says take the derivative of the top and the derivative of the bottom, then try again. Well, we all know those derivatives are growth rates. Oh, kitty cat's coming in to say hi. Hey, Noah. Yes, you're beautiful. No, you cannot be here right now, baby girl. I'm sorry. I'm sorry. I know. You're grumpy. It's okay. Go be grumpy somewhere else. It's okay. It's okay. All right. So, who grows faster? Who grows faster? They kind of look like they grow at about the same speed. It's not immediately obvious. Let's find out. So, of course, at a glance, if you just plug in infinity, this would be like the natural log of infinity over the square root of infinity. And we've discussed this before. The natural log of infinity is infinity. He does grow unbounded, albeit slowly. And the square root of infinity is also infinity. There is no finite number you can multiply by itself to get infinity. So this is an indeterminate ratio, which means we can go ahead and smack this thing with L'Hopital's rule. And remember what L'Hopital's rule says if you get an indeterminate ratio, either 0 over 0 or infinity over infinity, when you plug in your limit, then you can take the derivative of the top, take the derivative of the bottom separately, no quotient rule, separate derivatives, and then try again. So upstairs here, the derivative of my numerator, the derivative of the natural log of x, that's 1 over x. Downstairs here, the derivative of the square root of x, maybe we want to step to the side for a minute to calculate that. If I need to differentiate root x, that's differentiating x to the 1/2. That would be 1/2 x to the negative 1/2, subtracting 1 from that power. So that would be 1 over 2 times x to the positive 1/2, like this. Now remember what we said last time, you could just try plugging in infinity for x again, but before you do that, we should always ask, is there some algebra we can do to simplify? Is there anything I can do to simplify this expression before attempting to take the limit again? And this time the answer is yes. So if I flip and multiply, then I'll have my 1 over x times 2x to the 1/2 over 1. That's lim x to infinity. The 2's just chilling. And then I'll have x to the 1/2 minus 1, x to the negative 1/2. right? Because this down here is an x to the 1. And we have this algebra rule that says like x to the a over x to the b is x to the a minus b. Sorry, I keep getting these calls. No, okay. Free real estate agents, dude. The real estate market in Gainesville right now is fucking nuts. I don't know if it's worse in other parts of Florida or better, but my God, it is bad here. All right. So one run of L'Hopital's rule gets me here. Flipping and multiplying by the bottom gets me here. Applying this algebra rule gets me here. The end result is that I do not need another application of L'Hopital's rule. This is the same as 2 times 1 over the square root of x. X to the negative 1/2 is 1 over the square root of x. And now as x goes to infinity, this is 2 times 1 over the square root of infinity. And like we said at the start, the square root of infinity is infinity. So this is 2 times 1 over infinity, which is 2 times 0, or just good old-fashioned 0. So the answer to the question we asked at the start, who grows faster, the natural log or the square root, is the square root grows faster. Right? The bottom grows faster than the top. That's why the whole fraction goes to 0. Okay, good warm-up problem. Let's try something a little more challenging. Any questions on this guy? Okay, good warm-up problem. Let's try something a little bit more exhilarating. Let's do something like that. All right. Oh, did we end up doing this the other day? I think this one, yeah, we actually did this as a special case of something else the other day. Let's try something more exciting. How's about, ooh, that looks fun. Yeah, all right, 49 looks good. Let's take a little peeky weeky at the limit as x goes to 1 from the right, natural log of x times the tangent of pi x over 2. So we got to figure out what the problem is here. And as always, the first thing to do is just imagine plugging in the limit and sort of see what happens. In this case, it does require remembering what the graph of the natural log looks like and a little bit what the graph of tangent looks like. Let's say recall. Natural log I did just have up a moment ago. Looks like this. And the graph of the tangent function, I'm not going to graph tangent of x pi x over 2. I'm just going to give you the graph of the tangent function itself. And of course, he is periodic. Same sort of business, continuing over here. Something along these lines. So if you just plug in your limit here, what do you get? Well, you'll have the natural log of 1 times the tangent of pi over 2. On the graph of the natural log function, this x-intercept right here, that's 1, 0. So the natural log of 1, this guy is 0. Everybody good with that? We're approaching from the right. So we're going down to that y value of 0. On the graph of the tangent function, this asymptote right here is at pi over 2. So as x approaches 1 from the right, the inside of the tangent function is approaching pi over 2 from the right. So the little guy you should picture walking along the graph there is doing this. So this first piece, the natural log piece here, is going to 0. And the tangent piece is going to negative infinity. If you want to, the proper notation for this would be tangent of pi over 2 with a little plus here to indicate we're going from the right, because x is going to 1 plus. If we're going to 1 from the left, then the guy would be going up here on this part of the tangent function, and that would give me a positive infinity instead. But whether this is positive infinity or negative infinity at this step does not affect what we're going to do next. Either way, you're going to have a 0 times an infinity, which is an indeterminate product. So how do we wrestle with those? Does anybody remember? What did we do with our indeterminate products on Monday?
Take one and put it under the other inverse.
Yeah, perfect. We shove one of those guys downstairs as their reciprocal. And it's up to you if you want to shove the natural log downstairs as 1 over the natural log, or if you want to shove the tangent downstairs as 1 over the tangent. I know it might look like the scarier of the two choices, but the tangent is actually nicer because 1 over the tangent is cotangent, which is also a nice function. So here's what we're going to do. I'm going to leave the natural log upstairs. And I'm going to shove the tangent of pi x over 2 downstairs. I'll take the time to write it out like this. It's 1 over the tangent of pi x over 2. But then before I go and do anything with that, this thing down here is cotangent. It's cotangent, and that's a nice function to work with. So this is the natural log of x. Still have our limit out front, of course, right? Limit x to 1 plus natural log of x divided by the cotangent of pi x over 2. And what I'm using here is the fact that 1 over tangent theta is the same as cotangent theta. So now I've taken my indeterminate product and rewritten it in a way that I hope yields an indeterminate ratio. We can check and see what we've got. If I send x to 1 now, the top will be the natural log of 1, which is 0. The cotangent of pi over 2 is the cosine of pi over 2 divided by the sine of pi over 2. So this guy, as x goes to 1, will be 0 over 0. And that's an indeterminate ratio. Right, because the cotangent of pi over 2 is 0, and the natural log of 1 is 0. So now I can apply my L'Hopital's rule. Right, differentiate the top and differentiate the bottom. The derivative of ln x is 1 over x. Who remembers the derivative of cotangent? So the full derivative downstairs is going to require a bit of chain rule, but just the derivative of the outer. What is the derivative of cotangent? Starts with a negative.
Cosecant cotangent?
Oh, almost. That's cosecant. So this guy is going to.
Negative,
Yeah, go ahead.
negative cosecant squared.
Beautiful. Negative cosecant squared, and then I leave the inside alone, pi x over 2. And then by the chain rule, I need to multiply by the derivative of the inside. Well, the derivative of pi x over 2, it's the same as pi over 2x. So that chain rule piece there is just going to give me a pi over 2 here. So that's the derivative of the top and the derivative of the bottom. And we're sending x to 1. So now as I plug in 1 for x, I get 1 over 1 in the numerator divided by negative cosecant squared of pi over 2 times pi over 2. Cosecant is the reciprocal of sine, right? So we can ask ourselves, what is cosecant of pi over 2? Cosecant of pi. Cosecant of pi over 2 is 1 over the sine of pi over 2. Remember from your test, cosecant is 1 over sine. Sine of pi over 2 is 1, so this is 1 over 1. So downstairs, what we have there, I'll write the whole thing. The top is 1 over 1. The bottom is negative 1 over 1 squared times pi over 2. Nobody writes 1 over 1 though. 1 over 1 is just 1. So this is 1 divided by negative pi over 2 like this. I suppose I should still be putting this in parentheses. Don't be sloppy. And now you do your normal flip and multiply thing with fractions. This is negative 2 over pi. Nice, solid, indeterminate product question. Anything you guys would like to look at more closely here? Okay, I'm going to grab some water. My throat is quite dry. I'll be right back and we'll look at more indeterminate powers. Okay. So anything we'd like to look at more carefully? The Mac daddy of these L'Hopital problems are always the indeterminate powers. So indeterminate ratios are nice. You can attack them directly. Indeterminate products, you turn them into ratios by shoving one guy downstairs. Indeterminate differences, usually going to have a common denominator or something like that. It will become an indeterminate ratio, but an indeterminate power requires a little bit of care. We looked at one example last time, which was just x to the x. I'd like to look at something a little more engaging, maybe number 60 is good. Yeah. So a and b are constants. And I want to find the limit as x goes to infinity of 1 plus a over x, all raised to the power of bx. And if you just try to plug in infinity, we get that this limit equals, well, a over x inside here, that's going to go to 0, right? Like 2 over x or 10 over x or pi over x. As x goes to infinity, this piece is going to a over infinity, which is 0. So the inside here is going to 1. But then bx, as x goes to infinity, bx is going to go to infinity, like 2 times x or pi times x or 10 times x. If you plug in infinity, that's going to go to infinity. So this is another indeterminate power. We saw the 0 to the 0 indeterminate power in our last example on Monday. Here we have the 1 to infinity indeterminate power. The way we attack this is the same way we did last time. We're going to, instead of working with this original expression, we're going to work with the natural log of that expression. We're going to take the ln and work with that. So if I take the natural log of the limit as x goes to infinity of 1 plus a over x raised to the bx, shove that whole thing inside the natural log. First step, pop out the limit. And this was that thing we discussed at the end of class last time. Is this black magic? No, not black magic. Just a theorem from earlier in the class that says limits can pass through continuous functions. So now I'll have the limit of the natural log of 1 plus a over x to the bx, all inside the log. And then I can use that property of logarithms that says a logarithm of some stuff raised to a power is the same as this power being out front. So this will become the limit as x goes to infinity of bx times the natural log of 1 plus a over x. Now you do have one homework problem that is like this. It's not as general. You have some specific numbers rather than constants a and b, but the procedure will be exactly the same. So I would take good notes here. If you try to plug in infinity for x at this stage, the piece out front here, bx, still going to infinity, a over x still going to 0. So at this stage, this will look like infinity times the natural log of 1 plus 0, which is infinity times natural log of 1, which is infinity times 0, because the natural log of 1 is 0, which is an indeterminate product now. So that's what's cool about this log trick. When you take the logarithm, you go from an indeterminate power to an indeterminate product. And we know what to do with indeterminate products. You shove one of the pieces downstairs as its reciprocal. Now, I don't know about you. Understanding that after we shove one of those pieces downstairs, we're going to have to take a derivative. I could pick to either take this whole natural log thing and put it downstairs as 1 over the natural log of 1 plus a over x. Scary to differentiate. Or I can take this bx and put it downstairs as 1 over bx. Much less scary to differentiate. So that's what I'll do. I'll take the bx term and put it downstairs, leaving the natural log of 1 plus a over x upstairs, rewriting the whole ratio, the whole product as this ratio. If we had done it the other way, it would be bx upstairs and then 1 over that natural log downstairs. That 1 over the natural log thing would be scarier to differentiate. If we plug in infinity at this step, the top is, this a over x is still going to 0, so the top would still be the natural log of 1. The bottom 1 over bx, that would be like 1 over infinity. And both of those, the natural log of 1 is equal to 0, and 1 over infinity is equal to 0. So finally, I have my indeterminate ratio. 0 over 0. I can use L'Hopital's rule now. That means I'm going to take the derivative of the top and the bottom. This needs to be done carefully. Let me come over to the side here. If I differentiate the natural log of 1 plus a over x, I'm differentiating a natural log where the inside is this 1 plus a over x. So I'm going to have 1 over 1 plus a over x, that's like 1 over u, times the derivative of 1 plus a over x, the chain rule, which is 0 minus a over x squared. Right, the derivative of a over x, that's a times x to the negative 1, would be a times negative x to the negative 2. That's where this piece comes from. That's negative x to the negative 2 times a. And then this is like my 1 over u. So the natural log gives me always 1 over u times u prime when I differentiate. The derivative of 1 over bx, similar to the a over x piece, this is the derivative of 1 over b times x to the negative 1, which is going to be 1 over b times negative x to the negative 2, or negative 1 over bx squared. So when we apply our L'Hopital's rule, the numerator is going to be 1 divided by 1 plus a over x times negative a over x squared. And my denominator is going to be negative 1 over bx squared.
Can I ask where you got the negative for the negative a over x squared?
Sure. Yeah. Let me tuck this in here. So when I go to take my chain rule inner derivative, that's the derivative of 1 plus a over x. Oh, sorry. Here. The 1 differentiates to 0. And then the plus the derivative of a times 1 over x.
I see now. Thank you.
Oh, yeah, no problem. It's this guy. Since we started writing it, let me go ahead and finish it. That's a times negative x to the negative 2, which is negative a over x squared. Yeah, so there's quite a bit of like derivative work going on here. We got to be super comfy with the chain rule, and even then, it's not a bad idea to step off to the side and write some stuff out. So as long as we're careful, we land safely here, which might not look like things are getting better, but they really are. Because you see, I've got a 1 over x squared downstairs and a 1 over x squared upstairs. Those are going to talk to each other. So I get limit x to infinity. This piece I'm going to leave alone. 1 divided by 1 plus a over x. This piece I'm going to leave alone. Negative a over x squared. This piece I'll do the normal flip and multiply thing. So that's negative bx squared over 1. And the x squareds cancel. Blam, blam. So one last bit of algebra simplification. I've got this piece just going to hang out. And then this is negative a over 1 times negative b over 1. That's just a times b. As x goes to infinity now, this a over x piece, as it has done before, is going to go to 0. So this piece in front here is going to be 1 over 1 plus 0. And then I have AB. And 1 over 1 plus 0 is 1. So this is just a times b. And we're almost done. If you step back and remember how we got started here, this was not the limit we were originally trying to calculate. We took the natural log. So the natural log of our limit is equal to AB. Sorry, I was just griping about the real estate market in Gainesville. It looks like the guy next door to me is selling his house. Makes me want to run over there and put in an offer before these people finish their tour. So what we've shown is that the natural log of the thing I want is equal to a times b. And if you exponentiate on both sides, on the left-hand side, you get back your limit because the exponential and the log undo each other. On the right-hand side, you get e to the ab. And that is the final answer. Cool stuff, right? Questions on this sequence of steps? Okay, I'm going to turn the share off for just 1 second. I want to take a quick peek at something. It's a little boring. We can start there. That's fine. That's not. All right. Let's turn the share back on. The new section for today, section 4.5, is about sketching graphs, curve sketching by hand. The procedure for this is to kind of put together all the different things we've talked about so far this semester, at least since exam 1. So derivatives and how they tell us increasing, decreasing mins and maxes. Second derivatives, how they tell us concave up, concave down, and inflection points. Limits at infinity and L'Hopital's rule, and how those things can tell us end behavior or horizontal asymptotes. Section 4.5. I'm just going to call curve sketching. And it really isn't anything new. It genuinely is just a summary of all the stuff we've learned so far. So to graph function f of x by hand, we seek, and I'm going to give you a list of things. First, you want to know any x-intercepts. And along with those, you want to know where f is positive and where f is negative. So I'll say, and a number line or sign chart for the original function f. Second, and let me make sure I'm doing this in the order your book does it, because I think they give these things in a slightly different order than my intuition usually does. Domain, intercept. Yeah, I'm gonna give this a little bit different. You want to know, I can include in this also, I guess, the domain. You want to know where your function is increasing and decreasing. And your extrema. All of this comes from a number line or sign chart for f prime. Third, you want concavity and inflection points. And all of this comes from a number line / sign chart, whichever you prefer, for f double prime. And then there is some other miscellaneous stuff. Under the miscellaneous stuff, I would include any symmetries, asymptotes, vertical and horizontal, holes, right? Are there any holes in the graph? What other sort of miscellaneous things should we be concerned about? Oh, periodicity. All right. This is a highly condensed version of what the textbook gives you. Once you know all of these things, and the most important thing are these 3 number lines or sign charts. Once you know all of these things, you can draw a very nice graph of the function f of x. If you prefer to follow the guidelines exactly as they're laid out in the textbook, I invite you to do that, but you will find that it takes much, much longer and you end up with the same list of stuff and the same picture. Let's close this with some light. So what I'm going to do now is start with a function that we don't really know very well. It's not a transformation of any of our basic parent functions. And without using any graphing utilities, we're going to come up with a very nice sketch of the curve. This works great for any polynomial, by the way. Polynomial is very fast. But let's take something that's not a polynomial, like x e to the negative x. I want to come up with each of these things. So first, to find my number line for f itself and any x-intercepts, that means I need to figure out where f of x is equal to 0. Right? It's the same thing that we've been doing for the first and second derivative. We're just doing it for the original function. This would mean x e to the negative x is equal to 0. You know that e to the negative x is never going to be 0. So this happens if and only if x is equal to 0. In other words, your only x-intercept is the point 0, 0. And then we want to know where is the original function f positive and negative. We've got an x-intercept at 0, and that splits this number line into two regions. If I test an x value to the left of 0, like -1, I get negative e to the -1, which is negative e. So we are negative over here, because f of -1 is negative e. And if I test something like +1 over here, I get 1 e to the -1, or just e to the -1, which is a positive number close to 1/3. So the original function f, whose graph I'm trying to draw, will be negative to the left of 0 and positive to the right of 0. And we'll have an x-intercept at 0 where we cross over the x-axis. Next, I want to know, where is my function increasing? Where is it decreasing? Where do I have mins or maxes? That means I'm working with f primed. And the derivative here is a product rule derivative. So this would be 1 times e to the negative x plus x times the derivative of e to the negative x, which is negative e to the negative x by the chain rule. If you factor out e to the negative x, this becomes 1 minus x e to the negative x. So where is this thing going to be equal to 0? Well, again, e to the negative x, that's never 0. So the only place this thing can change sign is at +1. So I sketch a number line for f primed. Maybe I'll put +1 right here. To the left of +1, I could test 0. F primed of 0 would be 1 minus 0 times e to the negative 0. That's 1 times 1. In particular, we are positive over here. That means my function is increasing to the left, decreasing to the left of 1. No, what am I saying? I said positive and I wrote negative. Yeah, positive, increasing to the left of 1, sorry. And if I evaluate this at some number to the right of 1, for example, 2, f primed of 2 would be 1 minus 2, which is -1 times e to the negative 2. So that's negative e to the negative 2. E to the negative 2 is positive. It's around 1/9. So this is around -1/9. In particular, it is a negative number. So we are increasing to the left of 1 and decreasing to the right of 1. That means I have a, all right, here, let's see, increasing, 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 decreasing, decreasing, decreasing. That means this is a max, right? Going uphill here, going downhill here. That max at x equals 1. If we want the ordered pair, would be 1 comma f of 1. That's 1 comma 1 e to the negative 1. 1 comma just e to the negative 1. So we have a max here. Those are the coordinates. Now we do the same thing with f double primed. That means I need to differentiate f primed, and this will also be a product rule thing. I take the derivative of 1 minus x, which is -1 times e to the negative x, plus 1 minus x left alone times the derivative of e to the negative x is negative e to the negative x. Let's see, if I clean this up a little bit, this is negative e to the negative x minus e to the negative x plus x e to the negative x, which is -2 e to the negative x plus x e to the negative x. And factoring out the e to the negative x, I get, I'll write it as x minus 2 e to the negative x. You could write -2 plus x if you want. It's the same thing, just looks better that way. So the second derivative changes sign at 2. Put 2 over here. This is my number line for f double primed. If you evaluate this at an x value to the left of 2, like 0 or 1, you get something negative times something positive, which will be negative. So we will be concave down everywhere to the left of 2. And we will be concave up everywhere to the right of 2, because if you plug in something like 3 or 4, this will be positive. And that means we have an inflection point here. And that will be at the ordered pair 2 comma 2 e to the negative 2. Again, that y value coming from the original function, just like with the max. So we have all 3 number lines. I should have said in our first step, the domain. The domain here is all real numbers, right? -infinity to infinity. X is polynomial, domain all real numbers, e to the negative x is exponential, domain all real numbers. So now I'm going to take these 3 number lines, really just the bottom 2, and get that shape of f number line. The other thing we want to do is look for asymptotes, poles, periodicity. Let me go ahead and do that before I cook up my shape of f. You can ask, does this function have any symmetries? Is this an even function or an odd function, anything like that? The answer there is no, this is not an even function or an odd function. The exponential, right? All exponential curves kind of have that same shape, and neither of them have the even function y-axis symmetry or the odd function origin symmetry. So we'd say there's no symmetry. Asymptotes. Well, there's definitely no vertical asymptotes because our domain is all real numbers. But when it comes to finding horizontal asymptotes, we need to take the limit as x goes to positive infinity and the limit as x goes to negative infinity. Think back to section 2.6. So the limit as x goes to negative infinity of f of x is the limit as x goes to negative infinity. And this is where your L'Hopital's rule stuff will come in from time to time, x e to the negative x. This piece is going to negative infinity. And as x goes to negative infinity, negative x here goes to positive infinity. So that's e to the infinity. So this is negative infinity times positive infinity is negative infinity. In other words, there's no horizontal asymptote that we approach on the left. If we look at the limit as x goes to positive infinity of f of x, that is lim x to positive infinity, x e to the negative x. The x out front is going to infinity, so that's positive infinity there. And as x goes to positive infinity, negative x goes to negative infinity, so that's e to the negative infinity. This is infinity times 0, which is an indeterminate product. So I need some L'Hopital's rule. I need to shove one of those pieces downstairs. And we actually did a version of this the other day with x squared e to the negative x. It's nicer to stick the e to the negative x downstairs because then he just becomes e to the positive x. This is x over e to the x. And now this looks like infinity over infinity. So I can hit it with my L'Hopital's rule. The derivative of the top is 1. The derivative of the bottom is e to the x. So this is going to 1 over infinity, which is 0. So while we do not have a horizontal asymptote on the left side, we do have a horizontal asymptote on the right side. The way I like to describe this step is with a little end behavior diagram, similar to the stuff you saw in college algebra and pre-calculus. As x goes to negative infinity, we're going down. So the arrow on the left side of this graph is going to go down. And as x goes to positive infinity, we are approaching this horizontal asymptote y equals 0. So this will be my end behavior or asymptotics. There's no symmetry. There was an asymptote, just one, a horizontal asymptote that we approach on the right. Certainly the function is not periodic. There is no periodicity. All right. So now what we're going to do is combine the information we've put together so far into a number line for the shape of f, right? The shape of the graph, like we did in our first example on Monday. So I'm going to draw one big number line where I'll put all the stuff from the f prime and f number lines. Let me pop 1 right here and 2 right here. Everywhere to the left of 1, f prime is positive, so we are increasing. And everywhere to the left of 2, so I can come in here and fill in the increasing. And then to the right of 1, we are decreasing. So I'll say decreasing and decreasing. There's the information from the first derivative. Everywhere to the left of 2, we are concave down. And everywhere to the right of 2, we are concave up. So in this first region on the far left, we are increasing concave down. That looks like this. In the middle region, we are decreasing concave down. That looks like this. And in the rightmost region, we are decreasing concave up. That looks like this. So this is the graph shape in each of those regions. Now we're ready to put it all together. We had a max at the point 1, comma, e to the negative 1. We had an IP at the point 2, comma, 2 e to the negative 2. And now we're ready to draw our graph. Don't worry too much about the scales. It's mostly about the shape. E to the negative 1, you know, it's around 1/3. E to the negative 2 is somewhere around 1/8. So this is like 2/8 is like 1/2. So maybe I'll mark here a 1 and a 2 on my horizontal axis. And I'll mark up here as like a 1 on my y-axis, because I know that these y values here are quite small, like 1/3, 1/2. So 1/3, 2/9, 1/4, yeah, 1/3, 1/4. All right. We know we have an x-intercept here at the origin, where we go from being negative to positive. That came from our very first information here, right? We had an x-intercept at 0, and we go from negative to positive there. So I can draw the graph crossing through the x-axis here. I know that we are, unhide this. I know that we are increasing concave down everywhere to the left of 1. So certainly over here to the left of 0, we should have this increasing concave down shape, something like that. We're going to reach a max here at 1. And then we begin decreasing concave down until we reach this inflection point here, where we switch to decreasing concave up. And we know we approach a horizontal asymptote y equals 0 as we go out to the right. So something like this is a good sketch of this curve. The max here, again, is 1, comma, e to the negative 1. The IP here is 2, comma, 2, e to the negative 2. The horizontal asymptote over here is the line y equals 0. And that's it. That's it. We can check our work. But I expect this to be pretty good. So here we go. Here's x e to the negative x. It depends on how zoomed in you are at what point and what your scales are like. But you see, going down over here, down over here, increasing concave down until we get to this max here, increasing concave down until we get to this max here. What is this max? 1, comma, 0.3 something. So let's see, is that e, comma, e to the negative 1? Oh, sorry, 1, comma, e to the negative 1. Yep. So there's our max. And then what about the inflection point? Looks like we go from concave down everywhere here to concave up over here, right? You see how it The concavity changes. We're definitely concave up here. But we think our inflection point is at the ordered pair 2, comma 2, e to the negative 2. Bam, looks perfect. So this graph would be a 10 out of 10. Perfect. Beautiful. And this is a somewhat challenging example, right? So this sort of thing goes very fast with polynomials, and that's perhaps where it's most useful. Also works fine for rational functions, trig functions. These steps, this procedure for sketching a graph, really rock solid. And if you're on a desert island and you needed a graph of a function quickly, this is how you should get it. Questions on any one of those 4 steps, any of the number lines, or getting the number line for the shape here, getting the asymptote, any of that stuff.
Can you repeat what you said about the symmetry and the periodicity?
Mhm. So f of x is x e to the negative x, right? So the question is, how do we know that this function is not periodic? And how do we know that the graph doesn't exhibit any symmetry? Periodicity for us, the only periodic functions we've ever seen are trig functions. And that is going to be the case throughout the calc sequence. If there aren't any trig functions in this thing, there's no chance that it's periodic. So not periodic. Let's say no trig implies not periodic. And then the symmetry, my argument there was that because the exponential e to the negative x, he doesn't exhibit any symmetry. All exponentials have the same basic shape, right? Either the increasing exponential or the decaying exponential. But if you want to check carefully, an even function would satisfy f of negative x equals f of x. And you can check. F of negative x would be negative x e to the negative x, which would be negative x e to the x. And we ask ourselves, is that the same as the original? No, not quite, right? Now there's a negative out front, and there's no negative in the exponent. Odd functions, those with origin symmetry, satisfy f of negative x equals negative f of x. So that would mean that this thing, negative x e to the x, would be equal to negative x e to the negative x. And again, this is not true.
Perfect, thank you.
Yeah, no problem. So you can check for symmetries, the even and oddness, using the kind of original algebra definition of even function, which is this, and the algebra definition of an odd function, which is this. That is the foolproof way to do it. Any other parts of this procedure that we want to look at a little more closely? All right, just for fun, let me see if we can get one more in here. I'll make it a polynomial so that it goes more quickly. But that is about a test level question like this. And I do recommend going through that in the way that I did. I think it's nicer. It's much faster than the way the textbook pushes you through this stuff. So oblique asymptotes we can talk about on Friday. But let's just grab ourselves a nice polynomial and see if we can sketch a reasonable graph of this thing. How about number 4 here? X to the 4 minus 8x squared plus 8. Is that going to be fun? Sure. x to the 4 minus 8x squared plus 8. Okay. So first our domain. So polynomial, domain is all real numbers. And if you want to solve f of x equals 0, that means you're setting this whole apparatus equal to 0. This means we're trying to factor a degree 4 polynomial, which in general can be quite tricky. But we're in luck here because all the powers of x are even. I can think of this as like u squared minus 8u plus 8. Or x squared squared minus 8x squared plus 8 equals 0. So let's see, I'm looking for two numbers whose product is positive 8 and whose sum is negative 8. I don't believe integers like that exist. So I could, this is going to be the bulk of the time, isn't it? I can think of this as u squared minus 8u plus 8 equals 0. And apply the quadratic formula in terms of u. So the roots there would come from u equals negative b plus or minus the square root of b squared. 64 minus 4 times 1 times 8 is minus 32 all over 2, which would be 8 4 plus or minus the square root of 32 over 2. Should be 4 plus or minus 32 is 16 times 2. So that's 4 root 2 over 2 is 2 root 2. So we have several x-intercepts. So we've got x squared equals 4 plus 2 root 2 and x squared equals 4 minus 2 root 2. So your 4 x-intercepts are x equals the positive square root of 4 plus 2 root 2 and x equals, I'll just write this as plus minus, and x equals plus minus square root of 4 minus 2 root 2. And these four numbers will go on our number line for f, the original function. How big are these? Well, 4 plus 2 root 2, 2 root 2, root 2 is like 1.4, so this is like 3, this is like the square root of 7, so plus minus root 7. I'll go ahead and use the calculator. Come on, Larry. Oh my God. Square root of 1 plus 2 root 2. So this number positive and negative. 2.6-ish. The square root of root 2. So plus and minus 1.8. That's all, plus minus 1.8. So your number line for the original function f, you'll have that negative 2.6-ish, negative 1.1-ish, positive 1.1-ish, and positive 2.6-ish. From the end behavior of this fellow, we see that he's going to be positive on both sides here. So this is going to be an up over here and an up over here. And then at each of those regions in between, it's a degree 4 polynomial with 4 roots. So each one has to be multiplicity 1. So here's your number line for the original function f. And these decimals are just approximations for these algebraic numbers. For f primed are increasing, decreasing mins and maxes. We get 4x cubed minus 16x, which factors as 4x times x squared minus 4, which factors further as 4x times x minus 2 times x plus 2. So the number line for the first derivative, we have -2, 0, and 2 as critical numbers. Again, we can use end behavior a little bit here. This is an odd degree polynomial with a positive lead coefficient. So it will be negative on the left and positive on the right. And then from the factored form, each is a multiplicity 1. So we will blink back and forth as we hop over those guys. That means we're increasing, sorry, son of a bitch, decreasing here, increasing here, decreasing here, and increasing here. So there's a min here, a max here, and a min here. The y values, we would find those by plugging into this original guy. I may issue that for the moment. No, we got the calculator out, let's do it. So this is going to be, let's see, at 0, that's easy, right? At 0, we've got just 8. At 2, we'll have 2 to the 4 minus 8 times 2 squared plus 8, which is, oh, that read as 82 squared, didn't it? All right, so 2 to the 4 minus 8 times 2 squared. Son of a bitch. 2 to the 4, get down out of there. Minus 8 times 2 squared. Down out of there. Plus 8. Could have done it by hand now. Negative. So this is at 2, negative 8. And because all the powers here are even, if you plugged in -2, you'd get the same thing. This is -2, comma, -8. Our second derivative stuff, f double primed, easiest to differentiate from this form would be 12x squared minus 16. And we can factor out a 4. That gives me 3x squared minus 4. And this can be factored as a difference of squares, as the square root of 3 times x minus 2 times the square root of 3 times x plus 2. So the places where f double primed can change sign are at 2 over root 3 and -2 over root 3 to get a feel for the size of those. It's about 1.15. -2 over root 3, 2 over root 3. And again, end behavior and multiplicities will save the day. This is a even degree with a positive lead coefficient. So the end behavior must be positive for the second derivative. And that means in here. And from these two number lines, I can draw the shape of f. Symmetries. Here, this is an even function. I know that this is an even function because of the observation I mentioned a minute ago. It's a polynomial where all the powers of x are even. There are no asymptotes of any kind because polynomial. And it's definitely not periodic because no trig. So then when it comes to the shape of F, I include all the numbers from the F primed and F double primed stuff. And we saw that 2 over root 3, this number is about negative 1.15. So I would put negative 2 on the left, then negative 2 over root 3, then 0, then positive 2 over root 3, and then positive 2. So I've got several regions here. And in each of these regions, I can describe the shape of the graph. So looking at the first derivative stuff, F is decreasing over here, then increasing, we blink back and forth, right? Sorry, decreasing to the left of negative 2. And then we switch to increasing as we hop over negative 2. We stay increasing until we get to 0. And then we go back to decreasing. We stay decreasing until we get to 2. And then we switch back to increasing. Regarding concavity, everywhere to the left of this guy, we are concave up. Everywhere between these two, we are concave down. Everywhere to the right of this guy, we are concave up again. So concave up, concave up, and then we're going to be concave down all through this region. And then we are concave up all through that region. So this is decreasing concave up, that looks like this. Increasing concave up looks like this. Increasing concave down looks like this. Decreasing concave down looks like this. Decreasing concave up, increasing concave up. We can string all this shit together along with the knowledge about the x-intercepts. Oh, and I should say we had our max was at 0.8. We had mins at -2 and -8. Min at 2, 8. The inflection points, I did not find the y values out, but I'm already dragging you guys over time. So let's just get this done. And we can hunt down those y values of the inflection points later if we want. Let's call this +2. We'll call this -2. -2 over root 3. We'll say is here-ish. +2 over root 3. We'll say is here-ish. I know that my end behavior is up on both sides. I know I have an x-intercept at like -2.6, -1.1. Let's see, which is right about at that inflection point. And then +1.1 and about 2.6. And behavior up on both sides. And then we string together the pieces. So I'm going to be decreasing concave down until I get to a min at -2. So, sorry, decreasing concave up till I get to a min at -2, something like this. And we're going to turn around. And we come increasing concave up until we get to this point, which is both an x-intercept and an inflection point. So we switch our concavity there till we reach this max at 0, 8. This one is at -2, 8. This one is 0, +8. And then by the symmetry, we just repeat the same thing over here. Or you could follow those things. So decreasing, concave down, x-intercept and inflection point here. We switch till we get to this min. We're decreasing concave up. And then we flip around. And there we go. So the guidelines are not so bad when used to sketch the curve for a polynomial. Right? It's still a meaningful amount of work. It's not a nothing thing. But the idea is you get a genuinely nice, accurate graph out of this, which otherwise we would need some sort of graphing utility for. Just for gits and shiggles, I'll go ahead and throw this into the good old 84. What was the function? X to the 4 minus 8x squared plus 8. Let's see what we got. Not bad, right? Not bad at all. So this is how you draw graphs by hand, right? This is, in a large way, this is the goal of the first like 200 years of calculus. So this is the output from a lot of formalism from Newton and Leibniz. And this is what your graphing calculator does. It is a little bit more sophisticated than what like an 83 or 84 does, but if you're using something like Desmos, Desmos really does do this sort of stuff. It's not just plotting points. The 83, 84 really do just plot points. But yeah, curve sketching, a little bit time consuming. There will be at least one problem on exam 2 that requires you to go through some number of these things. Maybe I'll provide some of the steps for you and then require you to draw the graph from the number lines, or maybe I'll require you to cook up the number lines but not draw the graphs. Certainly practice these. There's a handful of them in your homework. Practice them earnestly. It's a very important skill. Also, being able to infer information from the graph about those number lines, being able to see the whole thing as a single picture and see how they interact with each other is a big deal. So I really enjoy these exercises. I hope you enjoy them as you work them. Please work them patiently. They do take a while. And if you're stuck on anything, don't hesitate to come ask for help. Yeah, Nick, if there's a video missing, I'll go ahead and take a look and make sure that gets up. All right, I've kept you guys past time. I'm going to go ahead and end it here. I hope you all have a lovely rest of your day. If you need anything from me, Canvas message, email, you all know the drill. Come by an office hour. Otherwise, I will see you on Friday. Bye, guys.